Hi everyone, so we're back for another video. So in this video we're gonna move on to the second step. So in the first step, when we want to add a new model to the Hugging Face Transformers library, we need to make sure that we can run a basic forward pass with the original model on some dummy input data. The next step is to actually fork the Transformers library under your own GitHub username and then clone it locally and run this command here. So that's what we're gonna do now. So I actually made like a figure of how forking and cloning etc looks like. So basically you always have like a official GitHub repository. So this could be like Dino v2 from Facebook Research, it could be Hugging Face Transformers and so on. And we typically call this the upstream repository. And then you can like fork it under your own name. So if you, for example, go to the Hugging Face Transformers repository, you can click here on fork, and then it will create like a fork of the repository under your own username. So for example, if I go here to the repositories and then here Transformers, this is my fork of the official Hugging Face Transformers repository. So this is like, you could say it's a copy of the repository under your own username. And then you can do git clone and then provide the URL of your fork, which you can find here. Well, it can be either using HTTPS, or you can also git clone using SSH. But in both cases, you just need to provide this after the git clone command, and then this allows you to load it onto your local computer from GitHub. So all of this is happening on GitHub, and then your local repository is just a clone of that. And so that's what they're asking here as well. So you need to git clone. Actually, this is a bit wrong here because we're saying git clone and then Hugging Face Transformers. Actually, you better first fork the Transformers library under your own GitHub username. So this would be not Hugging Face, but your own username, and then you can move to the Transformers folder, and then this will basically make sure that you have an editable version of the Transformers library. So the E flag means editable, so this means that if you update anything to the repository, you can directly try out the new features that you're implementing. And then this dev thing here means that we're gonna install a dev version of the Transformers library. So if you go here to setup.py, you will see that the dev version actually installs a bunch of extra dependencies, a bunch of extra Python libraries. Like for example, it will make sure PyTest and so on are all installed on your local system, because that will make sure that you can then also run the tests and so on. So yeah, these are like the first steps that you need to do in your local environment. So the first step is to fork the Hugging Face Transformers repository under your own personal username, so that it looks like this. So for that, you first need to go here and then click on fork, and then it will appear under your own personal username. Then you need to git clone it. So for that, you can provide the URL here locally. So then you can just do git clone and then the URL, and then move to the Transformers folder. And then actually I'm using this command to make sure it can open in VS Code. And then we can start developing on it. And so in this second step here, so maybe let's elaborate this a bit. So first fork the repository under your own GitHub username, then git clone it to your local computer, then do cd transformers, and then do pip install e, and then the dev version. So first, like this is also explained online if you don't really know what this means. But this is something that you may need to get used to This is like the typical workflow when you want to like develop on a new repository on GitHub. It's always first forking it under your own GitHub username, then git clone it to your local computer, and then oftentimes make sure that you have a dev version of it installed. So I also have that here, and then you can actually run this command, this transformers-cli add new model like command, because that one is actually what we need when we want to add a new model, because this is like a cookie cutter. It will basically provide a lot of the boilerplate that we need to implement when adding a new model. So it will first ask a bunch of questions, like what is the model you would like to duplicate, because oftentimes when adding a new model to the transformers library, it's almost all the time based on some other model that already exists in the library. So in this case, for example, when we want to add the Dino V2 model, we're going to provide here the vision transformer, because Dino V2 is basically a vision transformer. But the reason we're adding a new model is that the transformers library has a philosophy where we're duplicating code rather than using things like inheritance for the sake of like having models very independent in the library, such that like even though GPT-J, for example, is a model that is very similar to GPT-2, we still duplicate a lot of the code such that these models are very independent and easily readable. And then we use a mechanism called copied from, which I will explain later on, that makes sure that code is consistent across different files or different models. So then what is the name with no special casing for your new model in the paper? So in this case, it's Dino V2. Well, I guess they use uppercase. Let's quickly check that in their paper. Yeah, Dino V2. What identifier would you like to use for the model type? So the model type here refers to, if you go to the configuration of any model, you will see here a model type. So that's what we would like to get for a new model. So it can just be a Dino V2. If you just type enter, it will take the default provided answer. What lowercase name would you like to use for the model folder? Yeah, Dino V2 looks fine. What prefix camel case would you like to use for the model classes? So I think in this case we're gonna go for Dino V2 like so, because then we will have classes like Dino V2 model, Dino V2 for image classification, and so on. But there is a error. That's weird. I think there was something wrong with the answer provided. Let me try again. Okay, now it works for some reason. Then the uppercase name, yes. Then the class name can indeed be like so. And there's still an issue. Okay, please give a checkpoint identifier. So this is like the default model. I think we can use Facebook/Dino V2 base. You can always change this later on. Will your new model use the same processing class? I would say yes for now. Should we add copied from statements? So here we are already referring to this copied from mechanism, which I will explain. Yes, and then yes. All right. So then it creates, like, as you can see, a bunch of files for you to complete. So as you can see, this is like the documentation. You need to insert a paper link and so on. So it will have created like a new folder here in the models directory, Dino V2. And then as you can see here, all the, well, I think we can already delete this one. We also just gonna need a single conversion script. Here I'm gonna also say here that it's gonna be meta AI. So yeah, Dino v2 model. I'm also gonna remove here already a bunch of classes which we don't need for now, like the form-masked image modeling. That's very specific to the vision transformer. We don't need that one. The for image classification one, I think we can keep it because it's, and then here I'm also gonna remove, so it also creates like an init file. So here we can remove the classes which we won't implement. Alright, then yeah, the configuration. So here also it can be, well, actually for the configuration we usually don't give an attribution because this is like implemented by Hugging Face itself. Alright, and then in the general init there's also a bunch of classes added here. So Dino v2 for masked image modeling, I'm gonna remove that one because we're not gonna implement that one. It was just copied from the vision transformer. Alright, and then yeah, let's go to the Dino v2 folder here. So as we have like a editable version of the library, we can just like already do this. Dino v2 config, Dino v2 model, and then we can already like create a configuration. So this will be like a default vision transformer configuration, and then we can initialize the Dino v2 model from that configuration, as you can see, and then we can already also print out the parameters. So as you can see, it looks like a basic vision transformer where we have like an embedding layer, and then we have these transformer layers on top of that. Alright, so now the next step, yes, basically to implement this script to make sure it like matches with the Dino v2 model that is present in the repository by Facebook Research. So that's of course a bit of the hard part, but that's yeah, indeed the next step. So once we have run this transformers-cli add new model like comment, you end up with like 14 files that are provided as boilerplate for you, and then yeah, we can start implementing the model. So that's step 3, start implementing the model in the Hugging Face format. So for that we're gonna actually yeah, work from the ground up. So if we go here to the Dino v2 model, back into the original repository, Dino v2, and then models vision transformer, you will see here, so they define a Dino vision transformer class, which is a regular PyTorch module. So they provide like a bunch of hyperparameters. As you can see, it will probably be a transformer consisting of 12 layers, 12 attention heads. This is the ratio between the size of the multi-layer perceptron and the attention layers, I guess, in the, or the hidden size, sorry, of the transformer. Then they define these blocks and so on, an interpolate position encoding method and so on. So the fourth features method first calls the prepared tokens with masks. So that's like the patch embedding layer. So I guess we can start with that. So as you can see, our Dino v2 model in yeah, so we have these copied from statements here. So what this means is that you can add like between different models in the Hugging Face transformers library, you can add on top of classes or on top of individual methods these copied from statements, and then if you run locally make fixed copies, it will basically make sure that yeah, all of the copies are checked, and this will make sure that the code is consistent. So this is like something we still use to make sure that if models are very similar to another, you can use this copied from statement. But as you can see, it also makes sure that the readme gets filled in and so on. So that's also something we're gonna need to take care of later on. But yeah, our Dino v2 model consists of an embedding layer, as you can see, and then an encoder followed by a final layer norm and then a pooling operation. So if we go to the original model here, so here I was running a basic forward pass with the original model. Well, we can maybe start with that one. So I think it only consists of like this patch embedding layer, which gets initialized here. Right. And then yeah, they define this class here for the patch embeddings to the image to patch embedding. So yeah, let's go back to our Excel draw and create another figure. So basically how a vision transformer looks like. Standard design of a vision transformer is that we first have like a patch embedding layer. So let's say we have an image of 2 to 4 by 2 to 4. Then we first prepare the image for the model. So typically, like in Hugging Face transformers, we call the input to the model pixel values. So this will be like a torch tensor of shape, batch size, number of channels, height, width. So if we send like a single image to it, it will have the following shape. And then this gets sent through the patch embedding layer. What the patch embedding layer does is basically it will convert this into a tensor that can be consumed by a transformer. So typically the output will be something called hidden states or embeddings of shape, patch size, sequence length, hidden size. Because that's typically what a, so let's call this a vision transformer. And then we have a bunch of transformer blocks repeated n times. So let's say times n here. But yeah, every transformer layer, also called block, gets repeated like n times. So the n here refers to number of hidden layers. So this is typically something like 12 or 24. But every transformer layer always takes in a tensor of shape, batch size, sequence length, hidden size. So in case of a base vision transformer, this is going to be, well, it could be like 512. Well, actually, for a bird base transformer model, this is going to have a sequence length of 512 tokens, because we typically use sequence length of 512 tokens. But in case of a vision transformer, this patch embedding layer, well, if we use a image resolution, so let's say our image here is 224 by 224 pixels. This patch embedding layer is going to like cut the image into smaller patches using a convolutional layer. So we will also see that probably here. If we go here, as you can see, it uses a convolutional layer. This is also something that is nicely illustrated in this animation. So here we take an image, we basically patchify it, as you can see, into non-overlapping image patches. Like in this case, we have 9 image patches. And this gets sent as one long sequence through a transformer encoder. And so this red block here in the figure, linear projection of flattened patches, that's what the patch embedding layer does. Basically converts our image into this sequence of patches, which can then be consumed by a transformer. So yeah, this sequence of patches, we call them hidden states. But yeah, if we use like a patch size, so every patch itself typically has a resolution of something like 16 by 16 pixels, then you can easily see that the number of total patches is going to be equal to 224 divided by 16 squared. So this is like, I think, 14 squared. which will be 196. So basically we will have 196 image patches, which are sent as one long sequence to the transformer, and every patch is gonna be embedded into a vector of size 768, typically for a vision transformer. So this patch embedding layer is typically implemented using a conv2d layer in PyTorch or in TensorFlow or another deep learning framework. But yeah, what this patch embedding layer does is converting our pixel values into these hidden states, also called patch embeddings, which have this shape. And so the 196 comes from the fact that we have a width and a height of 224 pixels, and we use a patch resolution of 16 by 16. But actually the number of tokens here that are sent through the model are actually 197 instead of 196, because we also have one additional special CLS token or class token. So let's actually verify that. So let's maybe go to our fork here of the DynoV2 repository, go to the forward features method here, and let's print out the shape of these tensors that get sent through the, well, actually we already had a print statement here, shape of the embeddings before the transformer. So if I go here to our notebook, as you can see here, shape of the embeddings is 257, so not 197, but apparently here it's 257 and then 768. So in this case it's gonna be, well, this is probably because it's using different image resolutions and different patch sizes. So maybe let's add that. So let's see what the patch size is. By default here it's set to 16 and the image size is set to 224. But probably when they define these new models here, like this DynoV2 model, as you can see, this one, well, it seems to also use the same patch size. So in our inference script here, oh, I see. Here the image size is set to 518 and the patch size is set to 14. So 518 divided by a patch size of 14 is 37 times, sorry, I need to square 37. Wait, that's not correct. So an image size of 518, patch size of 14. So 518 divided by 14 is 37. I'm wondering how they get to 257 sequence length. So for that, what we could do is go to the patch embedding layer here, and let's just print out the image size. Let's print out the patch size. All right. And then, yeah, of course, your patch height and width needs to be divisible by the height and width of the image. So yeah, I'm just gonna add a bunch of extra print statements here. Yeah, I'm gonna remove this print statement here, this as well. Yeah, okay. So I'm gonna add some print statements, push them to my clone, and then I'm gonna rerun this. So this is just to debug like what the well, probably it's probably the image size that is being used here is not 518. Oh wait, I think I know why. Yeah. Because the image that we are preparing here for the model, we're first, this was just defined by us. We were resizing the shorter edge of the image to 256 pixels. Then we are center cropping to 224. So yeah, the reason we're getting here 224 divided by the patch size of 14, which is 16 times 16 plus 1. And that's how we get to the sequence length of. So this here in our case, it's gonna be 257, and the reason for that is we are using here a patch size of 14. Which means that the number of total patches here is 16 squared. And then we add 1 for the special class token or CLS token. Alright. But yeah, I'm wondering because they are like the authors, they seem to define the model here. By default, they are setting the image size to 518 apparently, and the patch size to 14, which means like we have a very high number of patches that get sent through the model, and this has like a high compute requirement. But actually we haven't really checked out the pre-processing code yet. Let's see if they provide that. They do provide a eval script. They probably define somewhere augmentations. Okay, here make classification, train, transform, and eval. So it seems that they are actually using a image size of 224 by 224 as well. So I'm not sure why they were setting it to 518. Not sure where I get this from. Oh yeah, because it was apparently defined for the models on the PyTorch hub. All right, so in that case, we can just start creating our Hugging Face model here. So let's maybe just commit here our first draft first. Push this to GitHub. Yeah, I also added a method here like interpolate position embeddings, but I'm gonna, for the moment, remove that one. Gonna remove the copied from here because we also don't need the mask token. That's something very specific to the VIT implementation here as well. Gonna remove this and this. So we're just starting here on the patch embedding layer. This I'm gonna remove as well. And this as well. Oh, that was too much. Right, and this seems that this is also not really used. I'm gonna remove every mention of, wait, which class is this? Dino v2. Yeah, I'm gonna remove this as well. I'm gonna remove the copied from here. Gonna remove this docstring. Alright, this can also be removed. Could be that later on we add this interpolation of the position embeddings, but for now let's focus on the simplicity. Also gonna remove this. This is something specific to masked image modeling. Right. This is the Dino V2 model. Yes, I'm gonna remove this copied from here as well. So let's go to Dino V2 embeddings. So our embedding layer consists of like our special CLS token or class token, then our patch embeddings or absolute position embeddings. I would need to check actually what type of position embeddings that the Dino V2 model is using. Let's check that. Position embeddings. As you can see here, we have what was 518 divided by 14 squared, which is 1396, and then we add 69 plus 1 for the special CLS token. So in total this model was pre-trained with 1370 positions. Alright, that's interesting. Oh, they do have a mask token here, but yeah, not sure whether it's needed at inference time. Then we have our patch embedding layer. Alright, so and here okay, gonna check whether I haven't messed up anything with the fixed copies. Changing something here, yeah, we had to remove another one. Gonna remove this here as well. Wait, not sure why this is still here. Alright, let's run fixed copies again. So yeah, the reason I'm not like directly loading the Dino V2 weights into our existing vision transformer model is because there are gonna be some differences like in terms of which type of activation function that is used in the feed-forward neural network and so on. So because of that, we're gonna add the Dino V2 model as a separate model in the library to make it really independent from the existing vision transformer implementation, which also has its own paper. So what I'm gonna do is so this is like the conversion script where we are like converting the original weights into into the hugging face model implementation. Let's check again the right. I'm just updating the conversion script here for some things we don't need. Seems that the patch size is always equals to 14. Oh yeah, the size of the architecture. So there are a couple of various sizes that these models come in. So there is a giant one. Okay, I'm gonna run the script now. So we're loading the original weights from the Dino V2 repository. Bunch of missing keys, bunch of expected keys. Yeah, so so what I typically also do when I add a new model to the library is create like a simple document, let's call it weights comparison, where I just compare like the weights of the original model with the ones from the Hugging Face implementation. So let's call it original parameters for original weights, Hugging Face weights, or yeah. So if you go here to our original implementation, you will see here that we have first those layers, and then in our Hugging Face implementation, we have the following names. So in this case it's called like so. And then we have the transformer blocks. And so every transformer layer here looks like this. In the Hugging Face implementation. And then we can do the same for the original implementation. So we basically need to now just remap these names. From these names to these names. So for example, this thing here corresponds to this layer in Hugging Face, and so on. This one. As you can see, the shapes also are not the same yet. But it's going to be fixed once we initialize it with the right image size and patch size. Then this mask token, I'm not sure it's needed for inference. It's probably only used during pre-training. And then we have these patch embedding layers. So yeah, what I'm gonna do is let's go to another model that I contributed. Go to the conversion script. I'm gonna use something similar as this implementation. So the first thing we're gonna rename are the patch embeddings. So original name is just CLS token, and in our implementation it's called embeddings.cls token. Then the other one is post embeddings, which is called embeddings.position embeddings in our implementation. And then the next thing is patch embed.approach. Those are, as you can see, not the best names, so we typically go for clearer names in the Hugging Face implementation, like embeddings.patch embeddings projection. Wait, embeddings. I'm just gonna copy over this name here. So as you can see, converting is also just renaming some keys. Patch embedding layer, and then we have the transformer blocks. So here we have a norm 1, then attention, projection, gamma layer, norm 2, fully connected 1, fully connected 2, LS2, layer scale probably. So that's not something we have in our implementation yet. But yeah, actually let's do this later on. For now, let's only focus on the patch embedding layer. Alright. So here for now I'm gonna say strict equals false. Missing keys, unexpected keys. Alright, so let's rerun this conversion script. Image size doesn't measure, yeah. I think we can remove that. But yeah, it's probably gonna result in an error. Yeah, because and that's where the interpolation of the position embeddings comes in. But so, as you can see here, we are already converting the weights. For now, it's only the embedding, the patch embedding layer. After that, we still need to convert the transformer blocks. But actually, one thing we could already do here is we can go to our patch embedding layer. So here, yeah, currently it's not, this is not working yet because the position embeddings are defined for 1370 positions, whereas we're only requiring here 257 positions. So, but one thing we can already do here is shape of the embeddings, printing that out. Let's see what this gives. And as you can see, it already provides like the same thing as we're having with our original implementation, which was here. So one thing you can now start to do is like you can go to the original repository here and add another, well, I'm going to remove these print statements here. But here we already had, like you can, for example, so let's remove this print statement for now and add it to the patch embedding layer. So I'm wondering actually how they are making sure. Wait, I'm gonna add some new print statements, shape of pixel values before patch embedding layer. Because then they have this projection layer. Shape of X after patch embeddings. So I just want to know, and I'm also going to remove this here. I don't want to see the entire tensor. So let's see. Okay, so the pixel values are still 224 by 224. But they are doing something with those position embeddings then. Okay, so the position embeddings are not yet added here. Post embed. Okay, here number of patches plus self.number of tokens. So yeah, number of tokens is set to 1 and number of patches is set to self.patch embedding.number of patches. I'm gonna add here a print statement. Okay, so wait, how are they then able to add the position embeddings? Oh, okay, so here they have this interpolate position encoding. So I'm afraid we're gonna have to add the same logic then. Okay. Gonna go back to the vision transformer. Yeah, I guess we need it, interpolate post encoding. I'm not sure. It seems to be very similar to the Dino V1. So yeah, I removed it, but I guess we will need it. But I think they interpolate by default. Yeah, they interpolate by default. So I guess we can also include that. So I guess I can remove this flag because we're gonna always interpolate. Wait. Okay, so it seems that now we are able to perform a forward pass already. So let's see. So yeah, all right. So yeah, as you can see, it's gonna be a bit different than the vision transformer implementation we already have in Hugging Face, because there, like, interpolation of the position embeddings can be done optionally, but for Dino V2 it's always done. Like, we're always gonna do the following here, as you can see. And this masks. Well, so next thing we could do to make sure we are converting properly is here. Let's. Okay. Layer norm is done after the flatten and the transpose. Flatten transpose here. Wait, do we already have a layer norm? So here they have a self.norm layer, if norm layer, else in.identity. Let's go back. It doesn't seem like they are using a layer norm. Okay. So yeah, one thing I'm gonna do now is like print out the first values of embeddings after the patch embedding layer. And we're gonna do the same in the original implementation. So then we can like compare whether we have the same exact values as our Hugging Face implementation. So now we can like rerun our notebook here or forward pass. We're gonna check like how what the initial values are of the patch embedding layer, and then we can do the same. Okay, first values here are the following. So now we can do the same for our Hugging Face implementation when converting the weights. And as you can see, these are now what we get. So make sure, of course, that we are both checking on our cat's image. So here we are preparing the cat's image. Actually, I should have checked whether the pixel values are exactly the same. Here we're using the VIT image processor, which is, well, it's also doing the same thing as the Dino V2. It's gonna first resize the shorter side of the image to 256 pixels, and then we do a center crop. Or not, wait, size. Okay, this one actually seems to default here to a... Okay, this one is not actually doing center cropping. Whereas our original implementation here, for that we're using this. First resize the shorter edge, then doing a center crop. Okay, I'm gonna use this for now to just make sure that we are comparing exactly the same pixel values. I'm gonna add here a width torch.nograd as well. And then here import from torch vision import transforms. So then we're making sure and as you can see here, this one ends in 0.0852. Let's see whether we get the same here. Yep. So that looks fine. So now we've already converted the patch embedding layer. So this layer here. And then the next step is gonna be converting these transformer layers, these transformer blocks. Alright, so I'm gonna already commit this and push it to GitHub. Convert patch embedding layer. Alright, so I'm gonna take a small break and yeah, then we can actually continue by converting the transformer layers, which come after the patch embedding layer.